Since I don't know if I should open this chat thing, maybe I can. Santosh, is there chat option open? Where is this? Here. Okay. That. Oh, what do I do? That these are, see, the very elementary fundamental courses, and some of you might have seen lectures that I gave on these topics last year summer school, which are all available on the YouTube. So did you or some of you or have seen that already, or should I go in that detail again, or at least for today maybe I can, but for next lecture and the remaining two tomorrow, maybe it is best if you have seen some of these and have questions. We can use this time to simply discuss your questions. That may be maybe more useful than me almost repeating, because the equations and methods and those things will be exactly the same. So can somebody write, or can they unmute?
We can go through those videos, from tomorrow onwards. Those videos we can just look into.
Yeah.
And I think if some additional features from solar physics is given, that will be beneficial.
Fine. I think that will be that is one comment, and then I can actually then at least cover something more useful, something like turbulent dynamos and that kind of a thing in say lecture tomorrow. And today I can just speed up and maybe just go in case something is not clear. For example, in today's, you can always look up the videos from the last year. So, okay.
Yeah. Hello. Am I audible? I just have a suggestion.
Yeah.
Yeah. Will it be possible to just give the links of those lectures, video lectures of last year?
I think it is summer school channel, or IUCAA summer school channel in YouTube. If you just type in YouTube, even the course name and instructor's name.
Okay.
Yeah.
Okay.
Even without the channel, if you just type the name and IUCAA and some instructor's name, everything
okay.
will.
Okay. Okay.
So, is there anybody else who? Okay, so I understand that many of you might be inclined that I can go fast, and that will be actually useful, so that if there is time, we can discuss questions that you may have. Is there somebody who wants me to go slowly and cover everything in detail?
Sir, hello, sir. Am I audible, sir?
Yes.
Please, my suggestion is, sir, can you please go slow and in detail, because not all the time we are having the opportunity to find all the lectures. So if you are planning for the lecture, in the same way, we can plan.
Actually, your voice is very broken. But I gather that you want that we go slow. Is that right?
Yes, sir. Yes, sir.
Okay, so I will take of course, if there is even one or couple of people who would want me to complete, then of course I'll do that. But in case you feel something is fast and something you didn't understand, maybe it is okay to just look up last year's lectures where things might have been said differently, although the equations and discussions, involved discussions, that will be identical, I can say. Okay? So if I have some time, I can cover something more modern topics like turbulent dynamo as part of, say, plasma physics. Okay. I have another announcement that tomorrow afternoon there is some emergency. So I will only take 3 lectures. Today 2 lectures and tomorrow morning. So tomorrow afternoon lecture will be cancelled. So and it is such last stage that I have not requested anybody else to replace me. So that can be a free time for tomorrow afternoon. My lecture that can be that is free time for you all. Okay. And I will try to do as much as possible in these 3 lectures. Okay, so let us begin. I understand your concerns and heard you. Fine. I think I'm going to start. I still see one raised hand, but I suppose this is from the last question.
Yes, please ignore that. I'm sorry.
Yeah. Okay. Okay, so this is a course on fluids and plasma physics. By now, you must have heard a lot on astrophysics and phenomenon in astrophysics, and you must have a fair amount of understanding of how one should describe and study these. You might already have heard words like Navier-Stokes equation, Euler equation, Bernoulli equation, and stuff like that. We will go very slowly towards deriving some of those. That is useful because along the way you will understand some of the very elementary aspects of how one should think about even basic um, medium like a fluid. Okay. Plasma, I will focus mainly on the macroscopic description, which is a single fluid plasma. So first you understand fluid, and then we'll go to single fluid plasma, which is a non-relativistic plasma in MHD approximation. Okay. So Magneto Hydrodynamics, which is basically relevant for a whole range of astrophysical objects. For example, the solar interior and solar physics, or accretion physics, all of these galactic physics, galactic dynamos or galactic fluids or interstellar medium, those can be described in a single fluid description in which the charges, positive and negative charges, are not separated, but in any small unit volume that you are allowed to take, it is charge neutral. But of course, this is a plasma, so charges can drive current, but without having any net charge in a small volume. Okay. So that will be the focus of the Magneto Hydrodynamics, which I will try that something else. I also had this slides last year's. Okay, so basically this is an online format, and it's very challenging to convey anything without any feedback from personal feedback from you all. So this is a very strange mode of communicating online, and for some topics it might be okay, but for some other topics this may be very tough. And this is very elementary course where a lot of discussion is possible once we are sitting together and trying to understand, spontaneously asking questions. Some of these things, for example, I may not be able to even watching if you are writing or something. I will not know you, right? So only towards the end I'll try. But let's anyway see that this is actually more important than the quote. This is taken from an article that appeared in American Journal of Physics, 1977. It's called Life at Low Reynolds Number by E.M. Purcell. So I will strongly recommend that you read this article by E.M. Purcell on life at low Reynolds number, and that can give you very profound insights into how fluids operate at low Reynolds number, and that is important to then distinguish it from the fluid at high Reynolds number. Okay. The quote is of course from Picasso, but this page appears on the last page of this issue. So, admittedly, it is very hard to teach in such format. There are some references which I will highlight right away that will be useful if you are interested in some of these topics. If you are interested in the basics of fluid dynamics, not necessarily even its applications, if you are, then you could just look up some of these Feynman lectures. The two excellent chapters: flow of dry water, flow of wet water. Ekeson, that's an elementary fluid dynamics. It's a very interesting textbook, very nicely written at a very elementary basic level, but covers a whole range of topics. And this Arnab Rai Chaudhary for fluids and plasmas, that's also a very nice book. Of course, Landau Lifshitz for more advanced reading. You could look up Landau Lifshitz. These are more at an elementary level, but this now will start to get more serious. There is also this book on physics of plasmas, and this is what I already mentioned. There was a video here. I don't know if I should show, but maybe I could just show. And just like last year's, I'll leave you to wonder. You just see that there is a water colored so that you can watch it. So just mix some turmeric powder here. And now I inverted the glass, okay? And you close the lid. You see, first of all, this is fine, right? This is not falling with the thing. Why that you can imagine, right? At this stage, water is not falling. So I hope you saw the experiment. Very simple, right? I mean, you take the water, yeah. You close the lid from above. Now, once you invert the glass, there is vacuum in the top layer. Now this part has vacuum. Okay. So there is a pressure difference. There is a atmospheric pressure outside, and that pressure difference maintains, and that's why this lid is not falling. Okay, or this paper is not falling. So there is a pressure difference. But now the question is, once you remove the paper, why did the water fall? After all, there was a pressure difference. Yeah? So the pressure difference that was making the paper stick to the glass, and the paper was not falling, and hence the water was not falling. As soon as you remove the paper, why did the water then fall? After all, the pressure difference is still the same, right? Okay, so you can think about it, what it is, and it's again an interesting question, and things like these actually happen in all sorts of mediums, right? From say, basically the fluid dynamics is very fascinating, and then various phenomena that you observe, various events that happen that you observe, they all involve fluid dynamics at some level. Yeah. Okay, somebody has raised hand. I think it's better to wait towards the end. Okay, I'll take this question, but I'd say that it's better to wait till end. Yeah, who has question? Somebody has raised hand.
Sir, the paper has fallen because of external force applied to the paper, right?
No, you think about it. Okay. Yeah, okay. It's not that simple. Okay. I mean, paper did not fall. I mean, you didn't see this properly. Paper did not fall. Paper was sticky.
No, we applied some external force to the paper. Then.
No, I removed paper.
Yeah.
We slowly remove paper.
We are removing means nothing but we are applying some force on paper, right?
On paper, but not on water. Why did water fall? The pressure difference is there. The answer is not just that. You can try to imagine a very adiabatic. This was shown in a very drastic way. You can try to imagine a very adiabatic, slowly moving paper, so that in an infinitesimal time there is no work transferred to the paper and this and that. The reasons are something else. There is an instability here. So if you understand properly all these equations and all, you can work out instability called Rayleigh-Taylor instability. If there is a high density water or high density medium above a low density medium, the system is Rayleigh-Taylor unstable. That happens all the time, right? In interstellar medium, you can be having a high density medium above the low density medium. The whole notion of above and below makes sense if you have gravity or some direction to point to, that this is above and this is below. Otherwise, there is no above and below, right? In a free space, empty space. Okay. So once you have this sense of above and below, and you put your high density fluid on top of the low density medium, that system is Rayleigh-Taylor unstable. How do you study this? So if you understand the equations and various things, you can work this out. These 3 lectures will not be enough to cover various instabilities and derive various relations, but these textbooks will offer you those. And this experiment was only meant to, if you are puzzled, it was only meant to provoke you that you are puzzled. And if you are puzzled, then you go back and read and find out for yourself, why did it fall? Yeah. Okay. And make an ideal this thing, that okay, it's an ideal experiment in which I did not even put my hand. Lid was there, lid was not there. By some God's magic, by some hand came and something removed. Why did water fall? So don't get into these nitty-gritties of what is happening in a very small level. Okay. There's a good reason. Like there is a high density liquid above on top of a low density liquid. Wherever this thing will happen, there will always be a Rayleigh-Taylor instability that is excited. You might have seen various times some fingers developing and stuff like that. Okay. So just Google all these Rayleigh-Taylor, Kelvin-Helmholtz, these kind of instabilities, or read these textbooks, and you'll find excellent, beautiful images of these instabilities. Okay. So in the interstellar medium, you have such inhomogeneous medium, mixture of various types of gases with various densities, all sorts of instabilities are excited. Okay? What you observe, okay, is the effect of those instabilities, because you are not really with telescopes resolving all those instabilities and all those scales where they are operating. You are basically, your resolution is very poor, but overall broad effect of those can still be seen. Water flow that you see from such falls, these are not laminar or very by laminar flow one means the simple flows that can be described or studied and understood. These are flows that are turbulent flows, because the Reynolds number, which I'll come to, what is it? But given that fluids and plasmas we are discussing so late in the summer school, by now you must have heard words like Reynolds number, and at least would have a sense that if somebody tells you that Reynolds number of the system is very large, all one means is that the system is turbulent. If Reynolds number is small, that means the system is more laminar, that you can perhaps try and understand. It's not necessarily simple, but you can still make some progress. And turbulence, as you also might have heard or known, that this is an unsolved problem. Nobody has solved turbulence as such, but we know that there is a erratic, chaotic type motions that emerge, and it's statistically random and stuff like that. Yeah, it's a loss of predictability, that you cannot predict the motion of a fluid particle from one instance to another if it is turbulent. Yeah? So all that prediction or predictability that you have so in detail learned in Newtonian dynamics, classical mechanics, that given a force on a particle, given its position and momentum in phase space, yeah, an applied force, everything is given. The trajectory is kind of deterministic. You can determine the trajectory of a single particle, say, in this thing. None of this will be true in, say, turbulence. Yeah? So it's loss of predictability. So these motions are turbulent. In fact, Reynolds number corresponding to when you swim in the water, that's also fairly large, and this is also not laminar. And you can see various splashes and the patterns that emerge, very random motions that emerge. This signature of turbulent motions. Reynolds numbers typically in, say, interstellar medium, accretion disks around black hole. You know that this is a binary system. There is a star, there is still an active star, and this is perhaps a black hole or neutron star. It could be jets, say maybe AGN. So, and you will be hearing a lot about these active galactic nuclei and this and that. There is a matter that's this is in a binary orbit. The matter forms a Roche lobe, and then you work out a two-body potential and stuff like that, and you see that, okay, because of some rotation and this and that, there is an accretion disk forming. How do you study these accretion? These are highly turbulent, very high Reynolds number. By high one means typically larger than 10 to the 10, 10 to the 20, 10 to the power 20. So these are the typical numbers of Reynolds number in astrophysics. Sun has Reynolds number of about 10 to the power 10. So very, very large Reynolds number, very, very turbulent motions. And anything that we see and find as very interesting, for example, convection in the sun, in the outer layer, which is transporting heat from inside to outside, these are all very turbulent motions. And then these turbulent motions drive other interesting things. For example, the magnetic fields of the sun. I'm just quoting sun, but this is true for ISM, like where magnetic fields are produced in the galaxies and stuff like that by turbulent motions. So once you have a plasma, you put them into a motion, there is a possibility that you can drive current such that it can produce magnetic fields can lead to other more interesting things like solar flares, prominences, coronal mass ejections. Words like these you must have heard, that nowadays there are threats from, say, full solar flares and corona that may come towards Earth, or they may intersect some satellite and they can disrupt our networks and stuff like that. All these things are happening because of, say, somewhat magnetic structures on the sun. Those magnetic structures are then ultimately produced by very turbulent motions. So again, there is a fluid dynamics, right? So all of these things ultimately involve a good and fair understanding of the fluid dynamics. And fluid is, by fluid one typically means fluid neutral gas or neutral fluid, not electrically conducting. By plasma, this is electrical. That's the only difference. In the universe, as you will find famously in various textbooks, they will write that nearly 99.9% of the known universe is in the plasma state. Okay, so there is a good reason to understand and read this. All the stars are in the plasma state. These are all in the plasma state. Yeah. So it's very, very small amount that's not in the plasma. So nearly 99% is in the plasma. So that's what people write. Okay. So let's first look at what the fluid is. What is the fluid? So the fluid, so imagine a medium. So these lines are basically showing some, if you can see my hand here and there. So then also, so it's like suppose I take a small sample of air in our room, the room you are sitting in. After all, when you switch on a fan, you can feel the wind blowing at your face, right? Yeah. Why is it happening? Okay. This you can actually describe in terms of fluid. It's a continuum. You don't have to actually go to a molecular level to say that there is one molecule that hit the blade and that came and hit my nose. You don't have to go like that. It's a continuum. It's a whole wind. Wind is a continuum type. So what is the criteria to define fluid? What a fluid is? So suppose you have a system of size L. This can be your room. Yeah? Or this can be a small parcel of a galaxy. This can be a small portion on a sun or accretion disk, whatever it is. And so the definition will be general in that sense, and also is applicable to your room. So if this is the system size, and just take a portion of your room where you draw some, just to mark that you are considering this area, I can draw a small volume, which we will later call a fluid particle. A fluid particle will be a unit particle in fluid. Of course, it's a deformable. Yeah, so it's a fluid. It can deform its shape. A fluid particle, as we will come to know, is the smallest scale that you can that you are allowed to talk about in the fluid dynamics and in any continuum description of plasma. You are not allowed to go below the scale at a molecular scale. Yeah. So what is the criteria that we can just take, and why do we do this? It's obvious, right? We have, say, in the room, Avogadro number of particles, 10 to the 26 particles. If you were to write equations of motion for those many number of particles, how many equations will you solve? If you were to write in a very particle picture, and suppose I ask a question, given a particle distribution, yeah, work out its later trajectories given this and this conditions and boundary conditions. Okay. In principle, you can always write very usual classical physics laws for each particle, yeah, and work out all the forces. But this is basically an exercise that you cannot really do, right? Not even with most modern supercomputers. You cannot do this. Even just for a small number of particles in your room, you cannot do that. But we are aiming to solve problems of galaxies and sun and so on, right? So we should have a description which goes much beyond the particle description. In a sense, low resolution, coarse-grained, low resolution physics. Some details will be lost, but of course, a continuum description so that we are able to at least study the system, that you can handle the system. Otherwise, you can't even handle the system. If you go and discuss the trajectory of each particle in your room, there is no way you can do it. So that's why this continuum description becomes useful. What happens that if you consider a small portion, we will call fluid particle. Suppose this is giving the very system size. We know that if there are too many particles, we think of center of the neutron stars. By now you know what neutron stars is, I hope. So if the particles are very close to each other, very, very close to each other, that the Broglie wavelength, yeah, is comparable to the interparticle separation. Suppose that is the case, then what will happen? The two particles are brought so close that the Broglie wavelengths are overlapping almost. Okay, and then the quantum effects will arise. So then this is no more a classical ideal fluid or classical fluid. This is a quantum fluid. Then. Okay, of course that you study in a quantum fluid dynamics, so quantum fluids, that is also possible. Fluid that we are mostly interested in, and for example, solar, accretion disk, interstellar medium, we are largely interested in ideal fluids. The densities are not that high, packing is not that close, and particles are sufficiently well separated. If n, small n, is the number density of particle, work out explicitly that if this is the number density, this to the power minus 1/3 is the interparticle separation. So this is something you should be able to work out immediately. Okay? So this is the interparticle separation. An average distance between two particles given small n is the number density of particle in any medium. Yeah? As I said, this is all applicable to your range of astrophysical objects, any fluid. Basically. What is a fluid is the question. So if the interparticle separation is much larger than the Broglie wavelength associated with each particle, yeah, then you would say that the quantum effects are not important. Now you are in this inequality gives you a classical limit. Okay. Now you are into the classical physics, but still you have a very large number of particles. You should do something useful with this. Now I consider a small unit fluid parcel, okay, like this, and say that that small fluid parcel is very large compared to interparticle separation. So what does it mean? That if I take a small packet of small enough volume element in the medium here, for example, in the room, it should still contain a very large number of particles. So a fluid particle, so-called fluid particle, contains very large number of molecules or intrinsic particles that constitute the fluid. So this becomes a unit cell. By unit cell, one means that any scale that lies below which is not accessible in the framework of the usual hydrodynamics. Okay, so this is your unit cell. This is your unit, and that unit should be much larger than the interparticle separation, so that there are a large number of particles in that unit cell. Okay, and that unit cell must indeed be much smaller than the system size. Okay? So, for example, if I draw a sun or say a accretion disk, I should be able to draw a pillbox, a very small parcel, which is much smaller than the system size, but it is still large enough to contain many number of particles. But now the problem is, if I have a system where the particles are not colliding, suppose you are thinking of a collision-less medium, where the particles travel large distances before they collide another particle. Okay? Suppose that is the case. An example could be stars in a galaxy. The stars do not collide. Their mean free path is very large compared to the size of the galaxy. Galaxy is about what, 20 kiloparsec? Yeah. And if the mean free path, what is the mean free path? An average distance a particle travels before colliding and hitting another particle. So that's a mean free path. So if the mean free path is large, what will happen? That at one instant of time, you may have, say, 100 particles, for example, 100 particles. Another instant of time, these particles are moving. They're all moving, random motions, this and that, influence of force or whatever it is. But they're moving. They're not stationary particles. At one instant of time, there are, say, 100 particles. Another instant of time, there will be a 0 particle. Okay, because they would have all streamed out of this small unit volume. So the whole idea of unit volume will not make any sense if sometimes it has 100 particles and sometimes it has 0 particles, sometimes it has 2000 particles. This idea will not make any sense because your unit cell has it's not robust. Then what do you do? It's then as bad as individual particles. So the criteria for fluid is that the mean free path must be very small. The mean free path must be extremely small compared to the unit cell size, so that within a smallest unit cell that you can resolve in fluid dynamics, as soon as the particle tries to leave the room, it collides with another particle and bounces off. Okay, so there can be a very shaded region. You can just shade. There is no sharp boundary. The thickness of the unit cell will be of the order of mean free path, because whatever particles and molecules are sitting at the boundary, they can stream up to a distance of mean free path, but then they will collide, and these are all random motions. So the overall number of particles, the average number of particles in a unit cell will remain conserved because there are a large number of collisions. So unit cell size must be much larger than the mean free path, and that indeed must be much smaller than the system size. So this becomes overall, this whole discussion gives you a description of fluid. If all this is valid, only then you are allowed to use the fluid description to study that system. Okay. For example, stars in a galaxy, you cannot write down the fluid laws, like the equations that we will discuss. Stars in a galaxy you cannot study, but interstellar medium, yes. So I'll just give you a number that you can work out. The mean free path is given by 1 by n, which is number density in that medium, and sigma is a cross section, which is a dimension of an area. So this is per unit volume, this is area, so this gives you dimensions of a length. So this is the mean free path is 1 by n sigma, and you look up and read textbooks to learn further if it is not immediately clear why this should be so. Okay? Then you can just look up the text. So given this formula, the typical number density in our room at usual room temperature is 10 to the 19. That's the number density per centimeter cube. Okay. Compare this number with the say interstellar medium. Yeah. So our room is far more denser than the interstellar medium. Far more meaning 19 orders or 20 orders of magnitude larger density in our room. Okay. So interstellar medium is actually the best of the best vacuum on the Earth, are much denser still compared to the interstellar medium. It is the best ever vacuum possible. The question is, how do stars form in such a way? There are no. It's a vacuum like best ever known vacuum on the Earth will give you still 10 to the 4 type density. So this is still 4 orders of magnitude denser compared to the interstellar medium. There are phases in the interstellar medium that you can also read or might have heard. Work out the mean free path. For the room, it is 10 to the minus 5 centimeter. Okay, that is why all this wind is blowing at our face and we can feel everything. And because our typical sizes, so look at your fingertip, and so these are like we are dealing with millimeters, centimeters. That's our resolution. The mean free path is 10 to the minus 5 centimeter. It's very, very small. So the air molecules in this room, they do not travel very large distance before they hit another particle. Okay, because of course the density is large. So what happens that the whole description of continuum fluid dynamics becomes valid for the room. Okay, air in the room. Okay. Interstellar medium is 10 to the minus 5 parsec. So it is still 5 orders of magnitude smaller than the 1 parsec. Galaxy size is 1 kilo, 10, 20 kiloparsec. So there is easily about 8 orders of magnitude difference, which is a large range of scale involved. So even for ISM, the fluid description will be valid. For stars, it will not be valid. That we can work out. Okay. So I hope this is clear what the fluid is, what is the defining criteria. Now we need something else. A fluid particle now can be in motion. So I can, instead of assigning velocity to individual particles that make the fluid, you assign a single velocity v to a whole unit cell or this entire fluid particle. So whenever we will write velocity field in the next slides, all we mean is that velocity field in space it's like it's a function of space and time, isn't it? Velocity field as a function of space and time. We are going to derive equation for this velocity. Okay. Whenever we mean this velocity or when we write this velocity, all one means it's a velocity assigned to a single fluid particle, not to individual molecules. So one has to be very careful. This fluid particle can be in a local thermodynamic equilibrium. You must wonder, how do you define quantities like pressure, density, temperature? Yeah. So the collisions, as you will keep hearing from now on, that collisions are extremely important to equilibrate the temperature in this small parcel, so that you can assign a single temperature to this, similarly single pressure and single density to this. So all of these become a field variable. They are all field variable. Okay. By field variable, one means that quantities that vary in space and time. Temperature varies in space and time. But at a given space and at a given time, you can assign a single number to an entire fluid particle, not to individual molecules. So that's a very important point. Now, how many variables we have? We have 3 components of velocity. We need one this thing. We have 3 thermodynamic quantities. How many equations do we need? We in general need 6, right? 6 quantities, 3 components here and 3 quantities here. Okay. But we will use equation of a state, so one is less, so we only need 5 equations. Okay. One for the density, one for the energy, and one for the velocity. And then relate these thermodynamic quantities by equation of states. Okay. So I hope it is clear that the idea of local thermodynamic equilibrium is critical. Collisions are critically important before you can even begin to talk about fluids. Okay. And these are all field variables, equations for which we should derive. Okay, now fluid is in motion. Of course, there will be some pressure difference between here and there, like the wind flowing and monsoon coming and this and that. So something is happening. How should we describe the system, right? Because the velocity is a field variable, it can change from one point to another point. The same wind that is blowing from there to here, the velocity is not the same at both these points, okay? Or any fluid variable is not the same. So suppose you consider a field variable, take it to be scalar here, it doesn't matter, right? I mean, even if you have a vector field here, it's a vector field quantity. For each component you can write and imagine each component as a scalar field. Okay, so they are all can be thought of as scalar fields. Think of a scalar field and we will try to determine its evolution or its derivative, because this field variable is being carried by a background fluid. Fluid is in motion, yeah, and it can be velocity itself, but it can also be carrying the temperature, or you can mix a dye in a fluid and that can be mixed, right? When you spray a perfume, you ask the question why perfume simply starts to affect others and others can smell it. What is happening? Yeah, the air molecules is basically through wind is carrying them across. Okay, so think of one trajectory. Think of 2 points A and B. Velocity at a point A is say directed towards this point. At B it is directed towards this point. This is a field variable. We want to know how the field variable f changes as you go from point A to B. So that is a question. You're trying to define your derivatives. What is df by dt? What is this df by dt in a fluid? Okay, so A is labeled as x and t. Bold x is x, y, z, t. It's a 3D quantity. Okay. Time is counted as 0d. Okay. So if something is varying only in time, you call it a 0d problem. And there are 3 dimensions, and 0th dimension is 3 in classical physics. Okay. B is separated, infinitesimally separated point, x plus delta x, t plus delta t. Okay. So in component form, we can write like this. F at A, that can be temperature. You can think of this as a temperature, or you can think of this as a density. Density at A is written like that. All of this delta x, delta y, if you expand, because the velocity at A is given by small b, so delta x can be x component of dx times delta t. These are all infinitesimally closed points, AB. They are just blown up here, but infinitesimally closed points. So the velocity at x direction for time delta t will travel delta x distance. Okay. Similarly for delta y, delta z. Okay. Delta y is vy delta t, vz delta t. Okay. So I can now write the field variable at B, which is basically field variable at x plus delta x, y plus delta y, z plus delta z, t plus delta t. And you Taylor expand this. And by now I think and you must be doing Taylor expansion routinely. So if you Taylor expand this quantity about point A, so Taylor expand the field variable at B about the point A. So how will you write? Fa, basically like this, plus delta t, del f by del t, plus simply delta x, but for delta x you substitute this. Similarly, you can write this. So convince yourself that this whole thing will give you. So what can I take? I can take fb minus fa. I take fa on the other side, divided by this delta t. okay, divided by delta t. So FB minus FA divided by delta t in the limit of delta t going to 0 is called a capital dF by dt, often denoted like this. But if you are careful, then you denote it in whichever way you want. This is called material derivative or convective derivative or the Lagrangian derivative. Okay, so this is the Lagrangian derivative of F as it moves with the fluid or under the influence of a fluid variable velocity. This F can be V itself. Okay. So clearly you can see this is a partial derivative, which is an Eulerian derivative. What is an Eulerian derivative? Eulerian derivative is taking a derivative of a quantity by sitting at a single point. What is a Lagrangian derivative? By taking the derivative of a field variable as you move along the fluid. Okay. So that's a Lagrangian. You trace the fluid, okay, fluid particle. I hope this is clear. And this is of course Vx del by del x, Vy del by del y, Vz del by del z can compactly be written as V dot nabla. Nabla is your usual spatial gradient operator. Basically, it's a gradient. Del by del x, comma del by del y, comma del by del z. So V dot product is there. So in general, now you forget about F. That was just used to motivate if something is changing. In general, your Lagrangian derivative can be written in terms of Eulerian derivative with, this is the so-called advection. By advection, one means the transport of the quantity by the fluid, or this is, you might have in math courses, you will say directional derivative or derivative of any quantity here along the direction of the fluid. So it's a directional derivative. Okay. Combining these two gives you a total derivative or a material derivative. Okay. So this is very, very important to understand. That's where also the non-linearity, everything will come for the this thing, for the fluid and turbulence and all that. Before that, I'll just say that we are interested, or we will at least deal with mostly ideal fluid, which does not exist in nature, but it's a very useful concept. There's always some dissipation, but it turns out that in astrophysics the dissipations are so small, or these microscopic dissipations are so small, that you can treat fluid in many circumstances as an ideal fluid, which is non-dissipating. That means if you've heard on viscosity and all, so it's a very low viscous, low viscosity. Okay. Viscosity and thermal conductivity are ignored. Okay. If thermal conductivity is ignored, you can imagine that if a fluid particle is basically like heated up, it cannot conduct away its heat. Okay. Becomes an adiabatic fluid element. So it entropy that is associated with a particular fluid element remains same at all times. Okay. Because there is no conductivity to drive the heat away. There is no heat exchange between different fluid elements. The normal component of the velocity vanishes on solid boundary. So this is the chapter 40 in the Feynman lectures. If you see, flow of dry water. The title itself is very interesting. Flow of dry water. Okay. Because of ideal nature, the flow, the liquid will not stick to you basically. It's a flow of dry water. And the boundary conditions for ideal fluid is only this, that whenever the velocity or the fluid particle hits a solid boundary, like a wall in a room, yeah, because the air in your room is an ideal fluid, okay? It's nearly an ideal. So if it hits a wall, all the requirement of a boundary condition is that the normal component should always vanish. Okay? It will modify for the real fluids. For viscous fluids, you will require all components of the velocity must vanish at any solid boundaries. Okay, there is no relative motion between the solid boundaries and the fluid motion. Okay, so that is called a no slip condition. Okay, here slipping is allowed because tangentially a molecule can just go tangentially on the wall, because that is allowed in an ideal fluid. It's the only normal component. We can't penetrate through. Okay. But both tangential and normal must vanish in a real fluid. Okay, so keep that in mind just for boundary condition. So entropy, you think this is S is a specific entropy per unit mass associated with a fluid particle. Yeah, you can think in terms of entropy also, right? You can invoke your second law of thermodynamics, Singh in terms of entropy. You can relate ideal gas equation of states with P, rho, T, and choose your variables that suits your current problem. Adiabatic concept is very close to you, that you know that by adiabatic one means that there is no change in the entropy. Yeah, dq is tds and stuff like that. So adiabatic dq is 0, so tds is 0. That means ds is 0. So that means, and when you say ds is 0, that t is supposed to be material derivative and not a usual derivative that you might be using in other contexts. Here, when you say even small ds, if it is written with a small d, not a del, then that small ds means material derivative. You have to include that v dot nabla term. So that's why this capital, I emphasize that here by capital D, but even if I had written ds by dt, you must assume a definition which is this. Okay. So the entropy remains conserved for a particular fluid element. It's totally adiabatic process. For adiabatic, you know the relation. Yeah, adiabatic equation of state P by rho d the gamma is constant, and that's why this whole material derivative is 0. You can verify that the entropy goes as log of P by rho to the gamma. Yeah, isn't it? PV by PV to the gamma is constant. That's what typically start. So this is the condition for ideal fluid. Let's look at how mass conservation gives you a continuity equation. So in a small volume, rho dV is the mass, right? Rho is a density, fluid density. dV is a small volume element. So rho times dV is a mass contained in that volume. If you have a bounding surface with a volume V, the only way the mass in that volume bounding element can change is by fluxes of the mass through the boundary. Okay, so you think about it. What does it mean? I have a bounding surface. This could be a bounding surface. Okay, now you can imagine a small volume element here. There can be mass flux outward. There can be mass flux inward. Okay. But now we are talking about in general in the fluid. This was for the fluid particle. We are not discussing of the mass fluxes within the fluid. Fluid particle is the smallest scale, but I'm just saying now you draw a big volume where your unit parcels are placed here and there. A fluid parcel, a fluid particle could just move out of that volume or could move inside of the volume. Only by this process of moving out or inward, the mass in that bounding volume can change. Okay? So the masses can change only through fluxes through the boundary. Okay, by flux, you know exactly this is the area element. How much is the mass flowing per unit area per unit time? So that is the thing you can work this out. Dimensionally, you can see that this is all consistent. Okay, rho times v ds. Okay, so ds is like the area element which is normal to the velocity. Velocity you can write in terms of dx or say dr by dt. So ds times dr give you that volume element here. dt gives you this dt. So that's basically the same thing. Okay. So this velocity is dotted with ds. Okay. If this is what you say perpendicular to each other, so ds, the normal vector. Yeah, how do you draw the normal vector to the area? So you have, it's a unit normal vector for an area element. Okay, so v dot ds is typically you can think as basically the angle between them is basically like 0. If that's normal, when v is perpendicular to ds, that means the tangential, then that means the flow, the particle is not leaving the area. Okay, so that's why this dot product is very important. So think of all the directions here. I can simply apply the Stokes theorem now, isn't it? So it's a converted from area integral to volume integral, which becomes divergence of rho u, and take on the other side, you get a continuity equation. Okay, so this is a continuity. This integral form can often be actually very useful, but this is the partial differential equation giving you change in the density, yeah, which can change through the fluxes, okay, the divergence term. Now you can open this. So you'll get two terms. You'll get rho divergence v plus v dot grad on rho. So combine the two, del rho by del t plus v dot grad rho gives you this d rho by dt, and take the other on the right hand side, minus rho divergence v. Typically, and also valid for the molecules, the fluid in this room, typically we are concerned with incompressible fluids. And I'll come to later that what does it mean. Incompressible basically means that typical speeds, if those are very small compared to the sound speed in the medium, then the fluid is largely incompressible. We know in principle that the air in this room can be compressed, but our motions are so slow that by the time you try to compress the air in a room, all the compression and everything has actually been washed away at the speed of sound, okay, which is very large, 330 meters per second in the room, and our typical motions are what? Yeah, hardly a meter per second. Okay. So if your speeds involved are much smaller than the sound speed, the incompressible approximation is pretty good approximation. Incompressible means the density, the material derivative of the density, does not change in that process. If that goes to 0, the condition of incompressibility is simply divergence of V equals 0. It's very useful that just by looking at the flow V, we know whether it's incompressible or not. So you don't really have to invoke density. Of course, density can be constant, like really constant, like water, or it can vary. I mean, after all, you must make sure that this is 0, not necessarily rho is really constant. So this is a good approximation when speeds involved are much smaller than the sound speed. So for example, the convective granular motion on the sun, surface of the sun, are still much smaller, are moving much slowly as compared to the sound speed. So incompressible approximation is okay for also the sun and various other parts. Okay. If it is not valid incompressibility, then of course you have to deal with the whole equation, the compressibility. That becomes a much harder problem. Okay. That becomes a much harder problem. Now let's work out the momentum equation. So for momentum, we have to work out the forces. One of the most important force that we will see is coming from pressure. So now you consider a unit parcel, again, a cube drawn here. If there is a pressure, as I said, there is a neighboring fluid parcel. You can imagine fluid parcel from all sides, okay? And this target fluid parcel is being pushed from all sides, okay? Now, where should it move? That will depend on all the resulting forces acting on the fluid. So what you are doing is to derive an equation of motion for the unit fluid parcel, for this fluid parcel. So of course, this is like F equal ma type equation, that how much is the acceleration given forces on the body. So one force is coming from pressure differences in the fluid. Okay. That is one of the reasons that why the wind is flowing, right? Is going from high pressure to low pressure, is being just pushed. Okay, but how do you think about it? So just look at a one-dimensional problem along x direction, and the same will hold for other directions as well. Okay. So if delta A is the cross section of one side, yeah, so P times delta A is the force by the neighboring fluid particle on this fluid particle. Okay, so this is trying to push this inward. So that is what P delta A Ex is a unit vector along x direction. Now on this surface, after all, force is a vector direction, right? So it's a vector. So for each direction, you just match the vectors, and then you have a right equation to deal with. Now the fluid on this side is pushing this fluid particle in this direction, in the negative Ex direction. That's why there is a negative side. Now if pressure at this point in x is P, you Taylor expand for a neighboring point which is delta x distance away. So if P is here, it becomes P plus delta P by delta x into delta x, right? So that's a Taylor expansion of the pressure. Yeah, I hope this is clear. If P at x is here, P at x plus delta x, you can write like this. Yeah. And if this is the pressure, I again multiply by the same area element, because these are neighboring points and same area element cross section is offered, delta A dx. Okay. So what is the net force working on that? net force along the x direction. So you take the vector sum of the quantities, vector sum, right? So this vector is pointing along this vector is pointing along this. Where the fluid parcel will move, it will depend on the vector sum of the forces. So vector sum will give you this plus this, because minus is already taken care of. So P first term will cancel off, and you only left with this minus delta P delta X delta. Now delta X into delta A is the volume element. So that's the volume element. Okay. So net force along X direction is minus this. And this you can now extend to Y and Z and write in general that the surrounding fluid will exert a force on the surface of the parcel, because the surrounding fluid cannot penetrate into the unit parcel, right? In unit fluid particle, right? Because these are the unit particles. Now they cannot really go through each other. So this particle has a pressure, this particle has a pressure. When they collide like cannonballs almost, right? That's one way to think, that they can only push the surface of the other. So how much is the surrounding fluid pushing the surface of this one fluid parcel? Based on this, you can guess the right formula, that this is the surface integral, closed surface, P hat n ds, and that of course you can use again the Stokes theorem, minus convert this P or the surface integral into a volume integral. So surface force per unit volume you can write as minus gradient of P. Okay. That's the term that has appeared here. Minus gradient P in x direction is just del P by del x. Okay, there is no shear stress in an ideal. That's why we will come to that later, that P becomes a tensor, and then you should worry about shear stresses. This is in ideal fluid is always a isotropic pressure, okay, and it's scalar quantity, and it will change once you go to the real fluids, because I could push the fluid sideways and there will be internal stresses that can be sustained through viscosity. Okay. So the momentum conservation is just like mass into acceleration, equal forces on the element, like surface force and body force. Body force is something like gravity. Okay, an example could be gravity. I can make an experiment in a gravitational potential. So I just simply keep on adding forces, which are the body forces acting on the whole body of the medium. Okay, so that you can just add at wish. Suppose you're doing the experiment in the vacuum. Okay, the pressure will be there, and body force you can typically suppose ignore. Acceleration is what? It's the total derivative or a Lagrangian derivative of velocity. So that's where you get this Eulerian plus v dot nabla v, the source of all the fascinating things. Basically, it's a non-linear term, v dot nabla v. That's where the equations become non-linear. We are now going towards Euler and eventually towards Navier-Stokes equation. And this is the source of all turbulence and written so simply, this is till date an unsolved problem. How to solve an equation that involves term like this. Okay. Now you consider a conservative body force, for example, gravity per unit volume. So you can write gravity force per unit volume is written say minus rho gradient of phi, stuff like that. Okay. This is per unit volume. In order to construct a per unit mass, all you have to do is divide this by rho density. Okay, so then it becomes per unit mass. Phi is already potential per unit mass. So momentum balance for an ideal fluid, this is an acceleration. So it's like on this side, mass you take on the other side. So write acceleration, which is force per unit mass. We know that this was force per unit volume. To convert it to force per unit mass, think about it, that you just have to do grad P divided by rho, and that then it becomes force per unit mass. Okay, so we are writing for acceleration, and you can minus 1 by rho gradient of P minus grad phi. If you have any body force, you can add another body force, like say Coriolis force, rotation coming from rotation, whatever forces that you want to otherwise add as a body force. It's the same thing. You have acceleration due to forces on the body. It's Newton's law of motion. Yeah. So this is the Euler's equations of motion, and we will actually use this extensively to learn a lot about the nature of fluids. One useful way to write this equation is to put them in a conservation form, where you have an Eulerian derivative of a density of a quantity. So suppose for mass conservation, you will write mass density. So this is rho. So you write density. For momentum conservation, you write momentum density. What is a momentum density? Is a momentum per unit volume. Energy. So for energy, you write energy density, energy per unit volume. So the conservation form has a structure like this: del del T of a density of a quantity plus divergence of the flux density of the same quantity is always 0. So you can always put the mass conservation, momentum conservation, and energy conservation into this form. Okay, so this is left as an exercise, okay, that you derive based on these things. You ignore the body force for now, and you derive this equation. This may be a simple and nice exercise where you will use the continuity equations to write the momentum equation in the conservation form. So it's a momentum density, yeah, and this is a momentum flux, right? If I have quantity rho, the flux is simply rho times v. That's the flux density. Okay. Similarly, momentum is rho times v. Put another v for a momentum flux of momentum. Okay. And that is same for energy. Here there is a quantity u, which is an internal energy of the fluid. I think for these lectures, I will not be discussing too much on the energy equation, but you should definitely learn how to solve this. Look up Landau-Lifshitz, for example, to learn more about the energy equation. This is an enthalpy of the fluid. So this is all coming from thermodynamics, which is internal energy plus P by rho. This is a specific enthalpy of the fluid that appears here in the conservation form. Okay. Equation of a state for perfect gas being used here is pressure is related to rho and density, R is your gas constant, which is nothing but Cp minus Cv. So these are things that you know, right? So that I will not spend too much time. So this is the equation of a state is given. Typically for incompressible fluid, you see the equation of a state is already divergence of V equals 0 is already the equation of a state. How many variables do we have? Now we have rho, okay, we have V, divergence of V can be used for an incompressible fluid to eliminate the pressure from this equation. Okay, so you don't need anything more for an incompressible fluid to solve the problem. Okay. But suppose there are this is not incompressible, you may also require energy equation, and then you use this and you can derive this. This is what? Kinetic energy and internal energy. How the kinetic energy plus internal energy, which is the total energy, how does it change as a function of time? That's where you derive by using the expressions of U. U is nothing but temperature. Yeah. So it's not very complicated, but it's a very useful form to derive. It's a generic form. Okay. And very immediate exercise. I think today I went very slow. I think in the afternoon maybe we cover because this may be soon going to be lunchtime. So maybe applications I will take in the afternoon. Okay, I will stop here. That these are the ideal equations in conservation form. The relevant equations are all given here. It's like momentum equation. This is the Euler equation, which will be actually most useful. Okay, and this is the mass conservation equation. Now we will make use of these equations to learn more about the fluid and properties. But I hope this derivation and everything was clear. How you derive is also, I think, clear. I've derived for 2, which is density and momentum, and third is left as an exercise. Only this is left as an exercise, energy. And this is not very hard. If you know both of these, you should be able to derive this nicely. So try this, and we'll meet at 2:30 for the next. To now look at the applications of this. Okay, so is there any question? So if you have questions, just raise hand. Otherwise, we'll meet at 2:30. Yes.
Hello, am I audible?
Yes, yes.
Okay. In fact, I had asked in the chart also this fluid parcel, or you can say the Lagrange derivatives of the fluid parcel. Are they defined only for streamline motion, or we can define them also for turbulent motions?
Yeah, it's a general definition. It doesn't distinguish between turbulence. So this is here. This is not a streamline. I haven't drawn a streamline here. I have just drawn a random. This could be actually a turbulent trajectory.
Oh.
So A and B are just infinitesimally separated point, and you actually are in some sense right that it is possible that we cannot even write the trajectory, but these are just infinitesimally particles. So I've just added, meaning connected them. Okay, but this is not necessarily a drawing of a streamline.
Okay. So you can define for any motion.
That's right. Yeah. After all, you are only doing some tail expansion. The only allowed thing, the only requirement here is that your field variable is Taylor expandable, that you are able to Taylor expand the field variable. Suppose the jumps are such that you cannot expand the Taylor this thing, then of course it will break down. By that I mean that suppose in a very infinitesimal times also,
yes,
if there are some sharp jumps and that you cannot define, then of course there's but that's the principle that Singh invoked, that the field variable that we are talking about, we are able to expand or make a Taylor expansion of.
Yeah, for example, within a very small time, delta t, if your velocities are also changing, for example, this vx, vy, vz may be changing. So
yeah,
in those cases.
Yeah, but that's where the assumption is that you basically go to such small times so that you can Taylor expand this. That's a condition on delta t. Ultimately, you are taking a limit delta t going to 0, right?
Yes, yes.
So in a limit of 0 time, it's very unlikely that there are such sharp jumps in space and time. So that's so. This is otherwise this is actually valid then for general field, and
But,
this is not.
I mean, this has been observed for any Reynolds numbers, etc. Or has that connection been examined or something? Or I mean,
what do you mean?
At any Reynolds number, this type of this what do you say, Taylor expansion is valid or not at any high Reynolds number?
I mean, this equation is valid only then. I mean, if that for any reason breaks down, then the equation itself is not valid, and then you of course will have to do something else to study that system. Yeah, the so-called Reynolds number and the motion of turbulence, that whole language is emerging from this term, which has been derived by this whole.
Okay. Yes.
So the basically when you say Reynolds number large or small, that for that we need viscosity, but essentially this term,
yes,
for which you have already used the Taylor expansion to derive this v dot lambda. This term is this because of the non-linearity, there is turbulence in the problem. And it can become, of course, in a finite time, the singularities could develop, but that's where the viscosity will come to rescue, because very sharp jumps that you may otherwise have will then be smoothed out by the presence of viscosity. That's where the viscosity becomes, no matter how small it is extremely important.
Right.
So that will make sure that there is some derivatives are possible. If the derivatives, you cannot take a derivative, then of course this description will not be valid.
Okay, thank you.
Thanks. Okay, so see you in some hours.